Thank you very much for the introduction, Tom, and thanks very much to Ushaw College for having me come and talk to you here. I would describe it more as a talk than a lecture. I'm not very good at the formal stuff, so you know it may go anywhere tonight. I do have a set of notes. I may not stick to them. I don't know. It's never clear to me until I've kind of got to know the audience a little bit. So we'll see how we go. As Tom sort of hinted, I would sort of see myself as a professional observer of science. After I finished my PhD, I moved into writing about science and the usual kind of writing about discoveries that are made and the progress that's being made. In recent years, I've moved more and more into writing observations, almost like I would sort of class myself as a science critic, much as the newspapers will have an arts critic or an architecture critic and a music critic. Nobody has a science critic, so I decided to fill that gap. And the book I'm going to talk about tonight, At the Edge of Uncertainty, is just another venture into trying to understand what science is doing and where it's going, and maybe the lessons that can be learned about what scientists are discovering and how they're discovering those things. Let me unpack the title quote first of all. So this comes from the great geneticist Jacob Bronowski, who's a real sort of idol of mine. He says, "Knowledge is personal and responsible, an unending adventure at the edge of uncertainty." And I think there's, and interestingly, he's not just talking about scientific knowledge there. In the Festival of Humanities, we need to acknowledge that, actually, I think this applies across the board. I'll be talking about scientific knowledge, but I think it can apply very much to the humanities as well. So he says that knowledge is personal, and I think it's a really important observation, that what you know and what you gain, and the ability to gain knowledge is a privilege, and you sort of you can take it on. Certainly, I know people in this room who spend their whole sort of professional lives gathering knowledge and enjoying knowledge, and I think it's important to always understand that knowledge sort of will depend on who you are and where you are. So knowledge is not an impersonal, abstract thing, which is sometimes an attitude that scientists certainly strike. They sort of gather knowledge and then it's knowledge for everybody. Knowledge is always personal. Knowledge is also responsible, and I think some of the things that I'll talk about tonight, and I won't go through all of the contents of the book, but I'll go through some of the areas of science that I think are really sort of most exciting at the moment. And I think what you'll find, and you may be horrified or shocked by some of the things that scientists are sort of exploring at the moment, and I think that's an important thing to make clear, that as scientists gather this kind of knowledge, they have to be responsible with it. And I think as society, it's very important for us to not just let science develop under its own steam and go whither it will, but actually have this sense of responsibility. And of course many of the scientists involved do operate a great sense of responsibility. Knowledge is an adventure, and it's certainly an exhilarating, exciting thing. Some of the things I'll talk about, they just sort of are quite able to blow your mind in a sense. The gathering of new understanding is an exciting thing, and I think it's very sad that sometimes when we teach our children in school about science, it seems to be incredibly dull and incredibly staid, and you don't get that sense of adventure that you might get actually in other classes. You do an art class and suddenly it's exciting, and you learn about these great artists, and some of them you can cut off their ears and things like this. And you learn, in science lessons, you learn very little about the excitement and the exhilaration of making a discovery, which is, somebody once said, I can't remember who, the greatest joy known to man is making a scientific discovery. It's also an unending adventure, and I think that's an important thing to realise, that this is something that whatever knowledge you gain, whatever knowledge you pick up, it's not the final answer. You would be a fool to think that you have the final answer on anything. And the history of science tells you very much that that's the case. But there's another side to adventures as well. Adventures can be dangerous and unnerving. And it's very important, I think, that we understand that adventures in science can often be very difficult for people actually involved in the scientific adventure themselves. There's a great quote from Goethe, if I've got it up here. So, daring ideas are like chessmen moved forward. They may be beaten, but they may start a winning game. So I wanted to kind of open up with this idea that we're going to talk about some daring ideas, but actually these are sometimes pursued at personal cost. And one of the stories that really makes that very clear is the story of a man called Ludwig Boltzmann, who I'll be able to show you a picture of him. He looks like a generic scientist, beard and glasses. There's one just here.
He's got more hair.
So Boltzmann had a crazy idea, which might not sound like a crazy idea to you, but his idea was that matter is composed of sort of these small blocks called atoms. And it wasn't even really a crazy idea, because the Greeks had pretty much the same idea. But at the exact time when he had this idea, when he was promoting this idea, it was quite unfashionable. It was unfashionable because it was around the time of the Industrial Revolution, and energy was considered to be the most fundamental thing at the time. So in physics, energy was very fashionable. And most of Boltzmann's colleagues considered the atom and the idea of the atom to be not where they wanted to go. In fact, the lucrative kind of science at the time was to do with energy, because you could then sort of help develop better and better engines. And if you could understand the principles of energy, then you would be a celebrated scientist. But Boltzmann had sort of worked out through another highly undesirable means, which is probability and statistics, that a gas in a bottle, for instance, would be composed of atoms, and that would be the means to explain how you got pressure and temperature and volume of the gas all interrelated. So, as you'll remember from school lessons, you increase the temperature and you'll increase the pressure of the gas in a fixed volume. Boltzmann had worked out the statistical kind of theory behind why this would happen, to do with the pressure on the walls and the movement of these atoms within the bottle. And so he worked it out to the point where he could explain all the observed phenomena to do with gases through his statistical means that gave these atoms a kind of reality. He said they must be real. They're knocking on the walls of a container, effectively, so they're real. And the thing was that Boltzmann actually was sort of very convinced of this, and sometimes very convincing. Boltzmann had what we would probably refer to now as bipolar disorder. So sometimes he was up, and he was very convivial, and students loved his lectures, and there would be queues outside the lecture theatre to get into his lectures because they were so great. And other times he would be down. And one of the things that always brought him down was the approbation of his colleagues, who insisted that atoms just could not be real. So they would talk about atoms, but they would talk about atoms as if they were a mathematical construct. So they would say, this is a mathematical idea that helps us understand how gases behave. It doesn't mean that atoms are real. And Boltzmann argued long and hard with people such as Ernst Mach here, who also has the beard and glasses for a generic physicist. It's a terrible thing. Please, if you're female and thinking of doing physics, you don't have to look like this. But a terrible, terrible example. And so Ernst Mach would argue against, and Ernst Mach and most of the Vienna group where Boltzmann was, would argue against him. And this weighed terribly heavily on Boltzmann's mind. He said at one point in one of these big arguments, Mach spoke out from the group and laconically said, "I don't believe that atoms exist." Boltzmann said, "This sentence went round and round in my head." And Boltzmann's head was never a very stable place. And sadly, in 1906, Boltzmann actually ended up taking his own life, partly because of the illness that he was suffering, but partly because of the turmoil and torment that this kind of attempt to put atoms onto the agenda of science really sort of took everything out of him. It was a very sad moment for science, especially as Einstein had the previous year actually just published evidence for atoms in terms of looking at Brownian motion, and Einstein's work was taken on and shown to be the path towards proving that atoms existed. So just a few more years, and the idea of atoms actually became very much mainstream. Although Mach, I think, went to his death saying, I will never believe in atoms, no matter what anybody says. A good, open-minded scientist. So this is the kind of the danger of science, if you like, as well. So things are not always as you want them to be. As scientists, you kind of explore the world, and I'm afraid you explore it through your prejudices as well. And Mac's sort of prejudices came very clearly through. But Mach is not actually alone in this. So you get people like Henri Poincaré on the right here, note the glasses and beard. So Poincaré was actually very close to understanding and delivering special relativity. In the end, he realized that if he was right in his calculations of understanding how space and time deform as things move fast through space, he noticed that you would get something that was later known as time dilation. That time was not a constantly flowing thing. That time the time observed for an object moving fast through space would be different for the time flowing of an object that's not moving in the same way. And this idea that time was this malleable, deformable, far from constant thing, as opposed to our daily experience of the clock sort of ticking on slowly through the day, was too much for Poincaré, and he decided to just leave it alone. And he kind of walked away from the whole sort of being on the point of discovering and publishing on relativity. He just walked away from it and left it for Einstein to do. Another example, and a very sad example actually, is the story of Subrahmanyan Chandrasekhar there on your left, and Arthur Eddington on the right. So Chandra was a very, very gifted mathematician and physicist who had very high hopes for his own career. He came over to the UK in, I think it was 1929. And on the way over, he worked out what would happen in the event of a large star dying and collapsing in on itself. It would collapse under its own gravity, and he did the mathematical equations and solved them to sort of find the end result. And what he found was that the collapse effectively goes on until the star tears a hole in space-time, as it were. So you get what we commonly know as a black hole. And Chandra thought this was an intriguing result. And when he arrived in Cambridge, he talked about this result to various people, including Arthur Eddington, who was the kind of premier astronomer in Europe at the time. And Eddington had actually sort of come quite close to seeing this same result of a collapsing star, but he thought it was absurd and would have nothing to do with it at all. And just sort of, when he heard about Chandra's result and that he'd worked it out mathematically and had all these things, Eddington actually gave him all the equipment that he needed to perform all the calculations that he needed to be able to present it at the Royal Astronomical Society meeting. And this was due to be a few months later at this time. And Eddington would come in and check that Chandra was doing well and work very hard to kind of make sure Chandra had everything he needed in order to present his result. And when the meeting finally came around, in fact the day before the meeting, somebody warned Chandra that Eddington had suddenly put himself on the bill at this meeting just after Chandra's talk. And Chandra sort of smelled a rat at that point, but carried on anyway. So he gave his talk about how black holes form. He gave his, his mathematical arguments for why you would get this rip in space and time. And it was all greeted and welcomed and accepted by the audience. And then when Eddington stood up to speak, his first words were something like, "Everything you just heard in the previous talk is complete nonsense." And actually sort of stood up there and decided from his prejudices that he didn't like the idea of black holes. He sort of destroyed the argument by making fun of the idea that something could disappear from space and time. And he just said, nature, of course, will stop such absurdities happening. Now, he couldn't actually sort of do anything about the maths, because the maths was right, and it worked very well. But he sort of destroyed the argument. And Chandra was so destroyed by this moment, he later said that this was the moment when he decided not to be a first-class scientist, but actually just to settle to be a second-class scientist, the kind of person who gives other people, data and ideas and doesn't bother with them himself. sadly, Chandra had to wait almost 50 years to get the Nobel Prize for the black hole work, partly because of the legacy of Eddington sort of making his life so miserable. Another interesting character here is a man called Benjamin Libet, who did the first neuroscience experiment to prove that humans don't have what we would term free will. I won't go into the details of the experiment, you can read about it just about anywhere if you Google his name. But Libet basically showed that you can read the signals from a brain that show a potential that shows an action is about to happen, a movement is about to happen. And that is actually before the person themselves is aware of making the decision to move. So you ask the person to decide to move their finger at a point that suits them. You have a clock running, and you ask them to record the moment at which, or remember the time at which they decide to make this movement. And actually, when you read the brain signals, you can see the brain initiating the movement at the time before the people themselves are aware of actually or say, making a decision to move their finger. So the interpretation of this experiment, and it's been repeated many times since, and moved on to extraordinary degrees, actually, with the sort of technologies of neuroscience. The interpretation is that people don't actually make decisions, but your brain makes a decision and then tells you about it. And the consciousness is effectively this clever illusion that gives you the idea that you have free will. Now, obviously, in a place like this, it's going to be open to questions afterwards. So, but we can, we'll probably talk about that all night. The interesting thing was that Libet hated his own idea and his own discovery. And so actually what Libet did was spend the rest of his life trying to find ways to refute his own experiment. So it doesn't always need somebody external to yourself to actually work against you, but it threw Libet into enormous turmoil. So, having brought the mood down very slightly, let me take it up a little bit. So here's a lovely quote, which I think sums up the whole of science. It's from a literary character called Lemony Snicket, which you may or may not know, who you may or may not know. Lemony Snicket says this in one of his books: "It is very unnerving to be proven wrong, particularly when you're really right, and the person who is really wrong is proving you wrong and proving himself wrongly right." And I've just never seen a pithier description of most people's life in science. You're constantly trying to work to find what the truth is. Your colleague's job is effectively to prove that you're wrong, or to attempt to prove that you're wrong all the time. And sometimes they're very good at it, and they make you look bad, even though you were actually right in the first place. And it can take years to get over this problem. And I think as I kind of go and explore a few of the ideas that are floating around in science at the moment, I think it's worth sort of keeping in mind that all of them may be wrong, many of them may be right, and we don't actually know yet. And this is kind of why I've put this on the edge of uncertainty, because some of these are ideas that seem absolutely insane, and some of them seem just slightly insane. So, before we go, just one quote from Erwin Schrödinger, who I think sort of sums up this, and I will sort of try and couch the things that we talk about in the terms of understanding who we are, because I think it's a really important observation to make about science, is that it isn't done for some, as I said earlier, for some abstract reason. I think what scientists are trying to do is understand humanity, and of course that's what the humanities are trying to do as well. So he said, who are we? The answer to this question is not only one of the tasks of science, but the task of science. And in the original, that's in italics. So this is Schrödinger's sort of summation of what science should be about. And so we have to ask the question, who are we? And one of the first ports of call for me is that if you believe modern science and the way things are going, certainly in biology, we are nothing special in evolution's eyes. So science certainly sees human beings as one of the species in the natural world, but nothing special, nothing sort of completely different to other people, to other creatures. Darwin said that animals whom we've made our slaves we do not like to consider our equals. And of course there are historical reasons for why we've chosen to sometimes consider ourselves above the rest of the animals. And it's interesting that science is now seeking to kind of claw back that idea. So animals, according to modern science, and when I say animals, I'm kind of saying non-human animals at this point. Animals exhibit consciousness, they exhibit personality, they exhibit culture, animals exhibit emotions and moralities. Animals display altruism, and they also teach. So there are examples in the natural world of animals that are genetically unrelated to other animals actually teaching younger animals how to do various tasks for no sort of genetic benefit. There's no sort of selfish gene involved in this. This is Jane Goodall, who started work in the very early 1960s. She was working as a secretary when she started to do field work in Africa, looking at chimpanzees. And she said, when in the early 1960s I brazenly used such words as childhood, adolescence, motivation, excitement and mood, I was much criticized. Even worse was my crime of suggesting that chimpanzees had personalities. And there's something in us actually that still, I think personally, that kind of struggles slightly with the idea of an animal with personality. And certainly if you work in the field of animal personalities, as many biologists now do, and are starting to be able to do more and more, it's seen as a kind of almost a slightly disreputable field because of the accusations, which were certainly leveled at Goodall, of anthropomorphism. But so in the studies of the Gombe chimps, for instance, Goodall would find that there were clear cultural differences between different groups of chimps. So in different geographic locations, some would eat ants or termites from a mound by sticking a stick in and then swiping off the ants with their fingers and putting the fingers in their mouths. Others would lick them straight from the stick. And they found that this was a geographical thing. It was cultural. It was in a certain group that's how you would learn to do things. Just as we would learn to eat. So, for instance, British people tend to eat prawns with the shell off. Singaporeans, I spend a fair amount of time in Singapore, will generally eat their prawns with the shell on, and it seems it's a cultural difference. It's quite horrible to me to have all that stuff crunching around in my mouth, but everybody to their own, as they say. And we're in a position where, for instance, the grooming behaviour of chimps is cultural, geographically separated. So you have situations where you have some chimps will pick a tick off another chimp's back and eat it. Others will slap it onto their forearm. And this again is a cultural thing. It depends on where you are. There are extraordinary stories across the animal kingdom of various different cultures. I think there's, I can't remember what slides I put in here now. So you have, these are dolphins of Shark Bay in Australia. And some of them use sponges to stir up fish and food off the bay floor. The only ones who do it, it's a very small number in their group, but the ones who do it pass it on to mother and daughter, and it's a mother and daughter thing. So if you are a sponging dolphin, then you will do that because your mother taught you how to do this, and others don't bother. It's a way of sort of stirring up the sediment without damaging your beak. And for some reason, some choose to sort of pass this on. Some choose to do this and some choose not to do it, but it's sort of done within family groups. There are interesting examples of the killer whales around Vancouver Island. There are sort of groups who live constantly around Vancouver Island, and they have certain ways of behaving. So they eat the fish, for instance, that are in the sea around there. And they have a certain dialect of their communications. But there are also visiting groups of killer whales that come. And these visiting groups, the kind of holiday makers who come around the island, actually they prefer the seals. And so they'll eat the seals around the area, and they actually have a different dialect they communicate in. So you can see sort of distinct cultural groups in the same way that we have, you know, cultural groups, and we have sedentary human populations and we have traveling human populations with very different habits and cultures. So, so there's, you know, a gathering and sort of growing number of examples of this kind of behavior. This is a bowerbird nest. And bowerbirds are fantastically interesting for so many reasons. But I think one of the most interesting things is the fact that young bowerbirds have to learn how to build these things. And actually they learn how to build them by practicing on sort of, they have mock bowers, effectively, that they build as young bowerbirds, young male bowerbirds. And the interesting thing is when they don't do a very good job, some of the older bowerbirds come along and show them how it's done. And it's quite an extraordinary observation that you know, it's sort of like, you know, helping out in a scout troop or something. You know, it's kind of almost volunteer work for the community. But they come and help the next generation of bowerbirds not to let themselves down very badly when it comes to mating. So you know, we have these kind of, you know, things that we used to think that we were in a position where. Oh, I'm going to go back. Sorry. There's a warning for later. You know, one animal is not the same as another, and what we see instances of animals displaying emotions and morality, but that doesn't mean that all animals of that species will display emotions and morality. And in some ways, this is a very difficult science to sell as a scientist because of the accusations of anthropomorphism, but it's becoming kind of irrefutable now that we're in a position where we can really, we really have to look at this and sort of examine ourselves in terms of how we deal with the animals and how we interact and what we consider to be our role on the earth as sort of co-inhabitants with these creatures. So we're in a position where, for instance, pollution in rivers will change the personalities of the fish within those rivers. So chemical pollution from estrogen, sort of ethinyl estradiol, for instance, which is found in contraceptive pills. When that leaks into rivers, studies have shown that three-spined stickleback actually become far more risk-taking animals. And so what you find is actually this only happens with the female population of these fish, but they take far more risks and they get predated far more heavily by pike in the rivers. And so you find that you have populations collapsing because of personality changes that are introduced by human changes. And if you never thought of a fish as being courageous or timid, wait till I tell you about the funnel web spiders. So there are actually timid funnel web spiders, some of the most vicious spiders on Earth, basically. But actually some of them are more vicious than others. And it depends on their genetics. And there are species that grow up in forests who can afford to be far more sort of risk-taking and venture out from their tunnels without sort of risk of being seized by a bird, and others who desert populations where if you venture out, you know, you're taking a risk, you've got to get your prey, but actually, you know, you're very easily spotted. And when you pit one of these sort of timid funnel web spiders against one of the sort of more aggressive and risk-taking and sort of big macho funnel web spiders, the results are horrible to watch. And so people have done these experiments and shown that the timid spiders are terrified by you know, other spiders of the same species. You know, they're not effectively, you know, all one sort of continuum, but they have different personalities depending on their genetics and where they're raised. And these kinds of things are starting to be used in conservation efforts. So you understand that you have a population of chipmunks in a national park in the US. Some of those will actually choose to stay away from humans, and some will be far more outgoing and interact much more with any humans in the area. And this probably doesn't come as any surprise to anybody who owns a dog or a cat in many ways. This is the funny thing about some of these issues that science is sort of facing, is that most of us have known this kind of thing for quite a long time. And science is sort of playing catch up in some ways, and trying to quantify these kinds of behaviours. But we all know if you own a dog or a cat that they have, certainly if you own more than one, that they have distinct personalities. And so Jane Goodall is now celebrated as a great scientist and a great naturalist. But it's worth remembering that in the 1960s she was absolutely derided for her thoughts on this. So I think there are strong implications for this, and I have to say that when I was writing the chapter of my book on this subject of how we relate to animals that show personalities and cultures, I kind of almost became vegetarian for a month because it sort of disturbed me so much. I'm glad to say I've recovered from that now, and I just don't go near that chapter anymore. So that's a good example from biology. Let me give you an example from physics. So we are holograms projected from the edge of the universe. There's one of my more ridiculous statements. Carl Sagan once said, "We are a way for the cosmos to know itself." It's an interesting, almost I would say pseudo-religious statement to make. But it comes from a sense that actually the consciousness that human beings have is something sort of above the order of inanimate matter and even most of the animals, and that we are exploring the cosmos. So I think that's where he comes from, is that as products of the cosmos, he famously said we're all made of stardust. So all the atoms within us, were once sort of out there in the universe, and now they've come and formed us, and we investigate the universe. So it's an interesting kind of perspective on who we are. But actually, you can go a little bit further with it. So you can think of the cosmos as a kind of human-powered computer, if you like, if you want to follow this. So there's an engineer at MIT called Seth Lloyd, who has calculated that a single atom can actually carry 20 binary digits, so that's bits, of information. And that when two atoms collide, the outcome can be entirely equivalent to processing that information. So the same as what happens inside the microchips of your computer. You can see it as the same process happening when two atoms collide. You can have the concentration of various chemicals involved in this, and you can sort of basically view the universe, if you choose to view it in that way, you can view the universe as a computer. Lloyd has calculated that a kilogram of matter can perform around 1 million billion operations every second. And that processing power is applied to about 10,000 billion bits of information. So since time began, he has calculated that the universe has performed around 10 to the 122, so that's 10 with 122 zeros behind it, operations on 10 to the 92 bits. And this is one way of looking at it, is information processing. The other way of looking at it, he says, is chemistry and physics. These are the processes of the universe, are exactly the same as the processes of information and computing. So perhaps this is a way for the cosmos to know itself. It's an interesting thing that we don't really understand cosmology very well. We don't understand the universe terribly well. And so you'll be aware of the Big Bang model, and you'll be aware of the fact that we have a universe that's expanding, and if you were to wind back time, you would find that the universe collapses in on itself to this point known as a singularity, where there is nothing. Now, nothing is a very difficult thing to kind of handle in classical normal physics. This kind of point of infinite density where the universe began, the Big Bang, is something that we can only understand with a theory that we don't yet have. This theory is known as quantum gravity, so at least it's got a name. And we're trying to sort of work out exactly how quantum gravity works. And one of the ways in which you can do that is actually to take a black hole and look at the physics of a black hole. And so you'll be familiar with black holes. They're sort of surrounded by an event horizon. They suck in all the matter that comes too close. Beyond the event horizon, there's no escape from the black hole. And everything sort of falls into a black hole from the sort of surrounding part. What is less known is that black holes actually also emit radiation. So they don't just sort of absorb everything, but they actually also spit out small quantities of energy, photons. This is known as Hawking radiation, after Stephen Hawking, who first conjectured that this must be the case. The interesting thing about a black hole then is that it gradually actually will spit out information, spit out photons to the point where it evaporates. So black holes don't live forever. Now, black holes absorb all this stuff, atoms or energy, and in the kind of modern parlance of understanding the universe as information, we actually can say that black holes absorb information, and they take in all this information that would encode how you build something like us. When the black hole evaporates, that information then is gone from the universe. And there's a fundamental law of quantum physics which says you cannot erase information, you cannot destroy information. And so physicists are left with a quandary where they believe that a black hole evaporates and disappears. And yet they say all the information that black hole has absorbed can't possibly disappear from the universe. So what's the solution? Well, that was arrived at by an Argentinian called Juan Maldacena in 1989, and he showed that if you have all that information actually encoded on the surface of a black hole, and at the event horizon, around the event horizon effectively, although there are more dimensions involved, which I won't go into now, then you find that actually you can keep that information on the surface of the black hole while everything else falls inside. And then when the black hole evaporates, the information is still there, so it hasn't disappeared from the universe, which is great and a great solution. And it's something that made Stephen Hawking actually change his mind about the whole physics of black holes. So impressive was Maldacena's sort of work. And then somebody else realized that you could take Maldacena's work and apply exactly the same geometry and equations to the universe. So you could say that all of the information that's inside of the universe, the information that makes up you and I, and all the atoms and all the energy, could equally be encoded on the surface of the universe. So if you imagine the spherical surface of the universe in many dimensions, which I'm sure you can, the spherical surface encodes all of the information that makes up you and I and everything else. And so the conclusion was that actually what we have is not this reality here. You know, you might think you're real, you might think you really exist, but actually you're just a projection of information that's held on the edge of the universe. So make of this what you will. But let me tell you that there's experimental evidence in support of this. Hard to believe, I know. So a man called Craig Hogan, who is the director of Fermilab, which is the US's sort of premier particle physics facility. Craig Hogan was looking at this idea, which is known as the holographic principle, that we project like a hologram. There's a picture of Princess Leia there from Star Wars, those of you who are familiar with that. And she is a projected hologram. That's not the real Princess Leia, just as Magritte said, ceci n'est pas une pipe. It's a projection, an image of a pipe. That's an image, and we are an image of something that's held at the edge of the universe. So Hogan was looking at this and saying, well, okay, so if that's the case, then actually we know two things about quantum theory. We know that you can't have infinitesimally small things. Actually, things exist in discrete lumps. That's what quantum is all about. That a quantum of something is the sort of smallest lump of it. And he also said there must be finite space to hold all this information at the edge of the universe. And if that's the case, then there should be a sort of limitation on the resolution of our reality. You know, what you see around us, if you were to zoom in with a microscope, eventually it would become fuzzy, just as if you zoom in on a photograph, you eventually see the pixels. So, it's no longer a continuous sort of a smooth image, but sort of pixelated and broken up. And Hogan said that if this holographic principle is right, then reality should be pixelated and broken up. And so if you zoom in on any particular thing or any region of space, you would eventually be able to see the quanta that make up these sort of discrete elements. And he did the calculation to find out exactly when you would see this and how you would see it. And he realized that the instruments that we've built to detect gravitational waves, which are called interferometers, and they're basically very good rulers for space-time. So they measure the extent of space. So they're very, very sensitive rulers. So if space sort of expands because as a ripple goes through a gravitational wave, then they will detect that. And he worked out that one of the detectors that we built, which is just outside Hanover in Germany, a detector called Geo600, he said that should have the resolution, enough resolution to be able to detect this fuzziness of space-time, the pixelation of space-time. And so he did his calculation, worked out what that signal might look like in Geo600. And then he phoned the director of Geo600, a man called Carsten Dance. And he said, explained why he was calling. He said, look, I was wondering if you've seen anything that looks like this, and sort of showed him the signal that he would expect to see. And Carsten Dance said, oh, thank God for that. We've been wondering what that was. And we haven't been able to get rid of it. And we had this noise in our detector, and it's been driving us mad. And Sagan said, well, actually, you know, what you're detecting is the fundamental nature of reality. and we're all holograms projected from the edge of the universe. Or I wasn't privy to the conversation. I don't actually know how it went. But, but we're in a position where Dance sort of took this on board and thought this was very strange, but he couldn't argue that was exactly the signal that he was seeing in this detector. And Craig Hogan has since gone away and built a sort of purpose-built detector to detect the holographic universe. It's called a holometer. He's currently testing it now, and hopefully we'll start to get results very soon. So I'm afraid we have experimental evidence that you're not actually real, and I told you we were going to go to some wild frontiers. So what else can we say about ourselves? A slightly more serious topic now, I would say. So epigenetics, which some of you may have heard of because it's starting to come into the forefront of our thinking. I very much like this quote from Steve Jones. From athletics to obesity and from genius to crime, the more we learn about genes, the more important the environment appears to be. So what am I talking about when I talk about epigenetics? So we've sort of been told over the last probably 40, 50 years now that if something's in our genes, it's our kind of inevitable destiny. And I have to say this is a kind of gross oversimplification. We've sort of each inherited a set of genes, but that doesn't actually determine who we are in sort of concrete terms. What happens is some of those genes can be switched on and switched off, and that will depend on the environment in which those genes are sitting. So, and that environment can be changed by things such as stress, things such as pollution, even just heat sensitive, the things that make the DNA uncoil and expose slightly more of themselves, and especially things like diet. So one of the ways this expresses itself is that the DNA will express proteins depending on whether the genes will express proteins depending on whether they're switched on or switched off. So they will build certain things in your body, but only if they're switched on. And there are certain things like stress and pollution and things in your diet that will allow them to be switched on and switched off. One of the dietary things is known as a methyl group, which is a group of carbon and hydrogen atoms, and that will attach itself to the DNA if it's able to, and it will change the way the instructions are carried out. So what kind of changes can this make? Well, interestingly, we're really at a very early stage in trying to understand what the changes are. But the changes, it turns out, are not just expressed in that individual, but can be passed on through the generations. So we're seeing, although in plants we've seen it for 30 or 40 generations, these epigenetic changes, in humans we've only seen it in 1 or 2. One of the most interesting things, you might recognize this woman. Anybody name this woman? Or tell me who she is? Do you see any genetic similarities? That's right, so it's Audrey Hepburn's granddaughter, Gold Star. And you'll see the kind of, there's an obvious sort of genetic relationship, and you'll see between the two of them. The interesting thing is that Audrey Hepburn was involved in what has become one of the great epigenetic experiments. So Audrey Hepburn grew up as Edda van Hemstra in Holland, and she was part of a group of people in a group of small villages who stood up against the Nazis and were helping to fund and support and feed and house resistance fighters. And Hepburn herself actually performed ballets to raise money to help the resistance fighters. And the community was punished by the Germans, who sort of isolated them and basically put them under siege and didn't allow any food to come through to these communities. And so many of them starved. It's known as the Dutch hunger winter. And during this time, any women who were pregnant at this time actually had offspring that had certain interesting characteristics. And what researchers have found when they looked at these, the offspring of women who were pregnant during the Dutch hunger winter, they found that they have an elevated chance of contracting breast cancer, of developing schizophrenia, And the other thing was, don't remember. And heart disease, sorry. So heart disease, schizophrenia, and breast cancer are all elevated in the offspring of people who were starved, whose parents were starved in the womb. The really interesting thing is that the same is true of their own children. So this passed down into the second generation. So we've seen these kind of changes. Interesting changes have also been observed in Stockholm. So a researcher in Stockholm actually in 1905, in 2011, went back to the Swedish agricultural record, which are kept very, very well, and they showed a sort of pattern of years of famine and years of plenty in Swedish rural communities. And he traced their sort of parents and grandparents of this time, and noted how much food would have been available to these people in these rural communities. And what he found was that, interestingly, a Swedish boy approaching puberty, who overate in a glut year, would actually risk reducing his grandson's life expectancy by 32 years. So not his sons, but his grandsons. So there seemed to be a correlation between overeating just before puberty and the resulting down the generations in a kind of reduction in life expectancy. There was another study that was done showed that if boys start smoking before the age of 11, the age when their bodies are just sort of starting to produce sperm, their sons will be significantly more overweight by age 9 than their peers who didn't start smoking. And there are these correlations that researchers are starting to tease out now. And the only sort of explanation for these correlations is actually that some kind of marker goes onto the sperm in these last two cases, where an epigenetic marker goes on and kind of changes the way proteins are expressed in the body in subsequent generations. Now this is still, very much work, as I said, at the edge of uncertainty. But we're starting to see that we can have detrimental effects if we make poor choices on not just ourselves, but in subsequent generations. So there seems to be some good reason to kind of take seriously the idea that what we do is not just about ourselves, but about our legacy that's passing on down. It's also, I showed in the first slide, an industrial estate. That's in Malaysia. And it was found that the people who worked on this industrial estate actually had epigenetic markers in their bloodstream. So they actually had DNA that was methylated by these methyl groups. And the problem that they all had was sort of breathing difficulties, which we're not surprised at living in polluted and working in polluted environments. But the methylation of the genes actually affected the gene for nitric oxide production, which is known to be a cause of asthma and wheezing. So we're starting to sort of tease out these ideas that it's not just about your genes, it's about the environment in which your genes operate. In some ways, a very young science, and also, I think, possibly with very far-reaching implications. I realise that time is marching on, so do you know what, I'm going to skip that one. And I will do two more. The will to live is something that we're all probably very aware of. There was a story in the Daily Mirror a few days ago, I think it was maybe Sunday or Monday, about a woman who had died in a nursing home, and her husband was also in the nursing home. And they'd been together, I think, sort of, the figures, 75 years or something, just spent their whole lives together. She died, and he died 10 minutes later. And we're kind of used to seeing these kind of stories pop up every now and then. And I think many of us have relatives that we know have died, after the loss of a loved one very quickly. And it's impossible for us to imagine how you can kind of somehow just sort of turn off like that. But it seems that there's very clear evidence that such things happen. And it's effectively because we're minds and bodies that are working together. And science has really fought tooth and nail against this idea, I have to say. So the idea that your mind and your mental state can have an influence on your physical body is kind of distasteful. Even now I struggle with it, to be honest, having sort of read a lot of research into it. And I sort of think, how can it be? How deep is this effect? And we're just sort of finding out. And so what we're sort of understanding is that much of the sort of ancient folk wisdom in some ways is right, that you need a positive attitude will make a difference. So for instance, there's a North Atlantic oceanographer's manual that says if you're caught in a shipwreck and you're shipwrecked in the North Sea and you're freezing, they said keep a positive attitude. It actually says this in the manual. Not that you would take the manual with you probably into the lifeboat. It does say first try and find a lifeboat, don't just think positive. But it does say if you find yourself in freezing water, keep a positive attitude because will to live makes a difference. And we actually know from experiments that simple mind tricks can suppress the immune system in animals. So you can have effect on people's immune systems and animals' immune systems. So in 1926, somebody did an experiment where they first taught rats to associate saccharin with a stomach upset. So they actually spiked sweet drinks with a drug called cyclophosphamide, which caused a stomach upset. And then when they just gave them saccharin, they were actually more susceptible to pathogens, so they would get ill more easily because their immune systems were effectively suppressed by the negative associations with this sweet drink. So they were more susceptible to sort of I think it was cholera pathogens that used on these animals than the animals that had been given no conditioning. Research carried out on 4,000 people over a 12-year period showed that a man whose wife has just died had a 25% higher chance of dying in those 12 years. But the interesting thing is that the bereaved reported twice as often, they reported heart and circulatory problems as people in the control group. So when your spouse has just died, in fact, you're literally heartbroken. The same is true in the dangers of loneliness. And there's been studies that show now that if you have adequate social connections, you're 50% more likely to live to the end of a specified period than those who are lonely, those who class themselves as lonely. And the researchers sort of put this as the effect of having good friends is roughly similar to giving up smoking or actually making a significant cut to your alcohol intake. Luckily, I have lots of friends that I go drinking with, so that works. And being chronically lonely, it sort of makes you almost twice as likely to die over any particular period. So there are various sort of studies that I talk about in the book that kind of seem to show, and also you can do sort of bizarre experiments. I'm not sure quite why people dreamed this up, but there was an experiment done on a group of women who were caring for their husbands who had Alzheimer's disease. So these are women in very stressed situations. And they agreed to take part in this study, where actually, as well as sort of having to care for their husbands, they were also given cuts to their forearm. So they I don't know why they agreed to this, but they did, and we should be grateful to them. The researchers would make an incision in their forearm and do the same with a control group of women who weren't stressed in the same way at all. And they would I don't know what the grant application looked like. I really don't. But so we're in a position where you could measure the time it took for their wounds to heal, and actually the women who were stressed, the wounds actually took far more time to heal. And when they took blood samples from these women, they found that their immune systems were seriously depressed by their stress situation. So we've got this sort of a plethora of studies that are starting to show that there are different ways of sort of investigating this link between the mind and the body. It's a field that's now known as psychoneuroimmunology. It's a sort of recognized field of science at last. In the 1980s, if you try and get something like this published, in fact there was an example of a paper that was put in for publication saying, we think there is a strong link between the brain and the immune system. And this was rejected in the 1980s by the journal Nature. And then when the researchers put in a similar thing about 10 years later, it was also rejected by the journal Nature, who said, well, this is self-evident. So there you are. So it's an interesting field that's just starting to kind of really take hold now. But it has great implications for our understanding of how to care for people, and of course the importance of social connections for people. If you have people in difficult and stressful situations, then actually that will affect their health. And again, in some ways, maybe not a surprise to anybody. So I'm going to finish by very, very quickly talking about the field of chimeras. And I think, it's sort of funny. It's also extremely serious. I really like that quote. If your parrot says, "Who's a pretty boy?" then that's okay. If a monkey says it, that's a very different matter. He said this on BBC Breakfast News. In fact, you can find it online. The quote's still there. It's just one of those moments you think, yeah. So the idea is really that scientists, and you will have views on this, I'm sure, and you should have views on this. Scientists can increasingly sort of see us, our bodies, as biological raw materials. We're used to this idea in some ways as blood transfusions, organ donations, and there's a growing move now to be able to mix together different species. So not just transferring from one member of one species to another member of the same species, the biological materials, but actually we're getting to the point now where we're starting to learn how to do things like grow a pancreas, so grow a rat pancreas inside a mouse, which has been done. And the idea, of course, is that if you can do this, then and do it successfully, then you can you could do something like grow a human liver inside of a pig and create organs for transplant. And that's a very inviting and enticing idea in an age where we struggle enormously to find enough organs for transplant. The waiting lists are huge. But there are, of course, enormous ethical issues about whether we want to do this. We have a kind of natural aversion in some ways, almost a natural disgust reaction to such things, to the idea of sort of mixing biological species. And it's an interesting thing for us to explore, that whether we need to overcome our natural reaction, or whether we need to actually sort of sanction this, or stop this research from happening. I'm undecided as yet, I have to say. There are ethical issues about this, and to be honest, the number of transplants that are needed would be enormous if you were to start to do something like this. But this is certainly something that scientists are being incredibly responsible about, I would say. So there are enormous efforts being made to understand the ethics of this, and to sort of really self-censor. So scientists have already stopped themselves doing some experiments that they know that they could carry out, because they want to know what people think, and they want to not act before anybody has sort of made up their mind about this. And so the idea of creating chimeras and creating sort of animals, a pig with a human liver, is something that in the next really few years I think we're going to have to talk to each other about and face up to whether we want this to happen, whether we want scientists to press ahead, or whether we think there are limits to this. And it's not something that I'm going to answer. I think these are decisions that we have to sort of make as a society. So let me just round up. I wanted to originally call this book Science is Slow. My publisher wasn't very keen on that. They said, who's going to want to read a book called Science is Slow? But many of the subjects that I've been talking about, and the other subjects in the book, actually have their roots a long, long time ago. So the idea of psychoneuroimmunology was actually dreamed up by Freud. Freud wanted to understand how psychotherapy might affect the brain, and he started a program in 1895 which he called the Project for a Scientific Psychology, and he abandoned it almost immediately because he realized that we didn't know anything about how the brain works, so what was the point? He then asked somebody to burn his papers on it, and they didn't, for which we should be very grateful, I think. So the idea of the will to live and this kind of exploring the mix between our feelings, our minds, and our bodies has been going on for almost 100 years. The idea of chimeras has been going on just as long. It was in 1910 that the first open attempt was voiced. The idea was voiced of mixing human and chimpanzee DNA together. So you would actually create a sort of hybrid chimp human, or maybe you could call it hemp, I don't know. So many of these ideas have been around a long time. The idea of information controlling the universe, of course, it feels quite modern, and you may think that actually, well, it just reflects, Newton lived at the time when clocks were very important, and he talked about the clockwork universe, and now we live in a time when we consider information and computers incredibly important, and now we're talking about the information-based universe. So maybe these are issues of our culture, but I think all of them are very interesting, and all of them sort of have the potential to turn into something where not only we're taken by surprise with these things, but scientists are also taken by surprise in what they're discovering, and these ideas are coming around again. Some of them have been disappeared and brought back again, and generally creating an exciting future. It may be something that you hear about these things and you think this is terrible and why are we doing it. Personally, I think that what's happening is science is opening up exciting and kind of wild new frontiers that scientists didn't see coming. And I think that's always to be welcomed, but it's now up to us, of course, what we choose to do with them and what we choose to allow to happen. So thank you very much for listening. I'll stop there.